Oh, welcome to the fifth session. So the seminar is going quite smoothly now, except for a few startup glitches when we are in person. So today I will be continuing my talk on higher connectivity. And I should actually close the window doors. So. And I'll go over what we did the last time because it is quite literally a continuation. So we started out with the definition of vertex and edge connectivity. Did that first result, kappa g is less than or equal to lambda g less than or equal to delta g? It's just the first result that you would do in this topic. Looked at some examples where we can make kappa g and lambda g differ as much as possible. And then, as a very nice corollary of that, we got that for three connected graphs. Actually, first, we were able to get a bound on M in terms of lambda, immediately followed by a bound on M in terms of kappa. And for three connected graphs, that becomes M greater than or equal to 3n over 2. And we have this starting picture for three connected graphs. Now, the rest of the talk is why we can start with 6 vertices and 9 edges, where we have just two three connected graphs, the prism and K33 drawn over here. So this is in a graph, in a talk on excluded minors, this is usually the starting point, but there's a whole lot of background that gets us to this place. So the first thing we did was the year decomposition theorem. That's an if and only if condition for G being two connected, right? And the idea is you start with a cycle and you add these paths successively to the graphs already constructed, right? And then from that, to prove that, we needed a lemma. G is two edge connected if and only if every edge lies on a cycle. From the next lemma we needed actually was G is two connected if and only if every pair of vertices lies on a common cycle. And then we started the proof. So this theorem, theorem 4, has a fairly long proof spanning several pages. Sorry, got a little confused here. So let's see. Lemma 6 itself is quite long. And then we have the theorem. So it spans about 6 or 7 pages altogether, this theorem. But it is a nice, interesting theorem. That's the year decomposition theorem. After that, we did Menger's theorem. And following Menger's theorem, we did not prove Menger's theorem. We proved Whitney's theorem from Menger's theorem. So Whitney's theorem says that G is K-connected if and only if there are K pairwise internally disjoint paths between every pair of distinct vertices. So after Whitney's theorem, we were able to get this condition. If G is 3 connected, then G has a K4 minor. So when you talk about 3 connected graphs, you start out with K4. K4 is the 3-wheel. Then we did a couple of excluded minor results, and I realized when I was going over these notes that I hadn't defined minor, so that's what I'm going to do when we start today. So theorem 11 was G is a forest if and only if it has no K3 minor. K3 is a triangle, and the intuition there is, well, if you don't have triangles, then it's acyclic, and therefore it has to be a tree. And then just for a technicality, we say forest, which is just acyclic and not connected like trees. All right. And then series parallel networks has no minor isomorphic to K4. So once you determine the class K3, class of graphs with no K3 minor, the natural question is the class of graphs with no K4 minor. And that is a three-wheel, and that is series parallel network, and the proof follows from all the above. So I think there's only one corollary that may not have been needed, but otherwise you need all of this stuff to get to this stage. And now let us continue. I'm going to begin with the definition of minor carefully, all right? So I've got in this today's talk, I've got some pages written up, but then other pages I will define carefully. And with apologies, Ming Shang, I know you know all this stuff, but I'm just doing it for the students. So let's talk about edge deletions. The natural thing, what you would expect to do in what edge deletion suggests is throw out the edges and leave the end vertices intact. So then edge contraction. So that's edge deletion, and that's the symbol G\E. Now, edge contraction is also a natural thing, also very intuitive language. You take the edge, right? So imagine an edge is a string, and you just identify the end vertices. Then you've got like this string that you just throw it out. Alternatively, think of it as a collapsible edge and identify the edge vertices. So if this is my edge E, then that's G contract E. You do get a multigraph here. So in papers in this topic, the graph always has parallel edges and loops, and then we say simple graph in all our theorems. Actually, in my book, I chose not to do that because I would be saying simple graph for every second theorem, and therefore it's actually opposite in my book. So if E is in a triangle, then you get parallel edges. And I just wanted to clarify something here, because you may have seen definition of minor as this. We say H is a minor of G if H can be obtained from G by deleting or contracting edges. And in my book and in other places, you may see deleting edges and any isolated vertices formed as a result. So they're really the same thing. We could just say deleting or contracting the edges, or the blue just hammers on this particular point that if this is the edge here and you delete it, then in the minor sense, you would also remove that isolated vertex, right? You have an isolated vertex here, and in the minor sense, you would remove it. However, we can just think of it as contracting the edge E, right? So then you don't have that extra clause to put. So many people will just say, and it's a little smoother to say, by deleting or contracting edges, okay? So just wanted to make a note of that little detail, because you may see the definition appear like that differently. So wanted to emphasize that. So now let's do clique sum. And just please stop me at any point if something's not clear. Arshia also, yeah. Stop me if something's not clear. Is this much clear so far?
Yes.
Yeah. And yeah. So a clique in a graph is a maximal induced complete subgraph. So I don't have an example here, so maybe just let's look at an example. So suppose I have this as my graph. So what's the largest one here, the largest clique? So there is, well, I could have actually, let's make this also. So this is a clique, right? That's K3, and that's maximal induced over there. You're not missing any edges. This one is also a clique, right? That's K4. Here, they're both maximal induced subgraphs, all right? So the K3, and sometimes we want to talk about the largest clique, but not today. All right, so if we wanted to talk about the largest clique present in the graph, then it would be K4, but not today. So K1 is just a vertex. So you can think of any vertex as a clique. K2 is just an edge, right? So you can think of an edge as a clique. And now let's talk about clique sums. So suppose your graph G1 and G2, they have a clique, right? Well, K1, K2, K3, and actually KT, right? Then the clique sum of G1 and G2 across KT is obtained by identifying the clique. So there's nothing more that needs to be said over there, but the word identifying the clique can lead to a little confusion, as in what do we mean? So it's actually, this is really show and tell. So you have your graph here, G1. You have your graph here, G2, right? And the G1 has a clique, G2 has a clique. You just like identify it, okay? One on top of the other. That's essentially what it means.
But having the same clique KT, does that mean isomorphic copies? They don't literally have the same clique because they're in different graphs.
Yeah. So, but when it's a clique, right, it'll look the same in both graphs because, so you're right. If you're talking about any subgraph, it can look very different here and look very different here. But clique will look the same, right, because it's complete. So you have a clique here, you have a clique here, just sort of slide it over and paste it. Okay, and we talk about, where did it go? Yeah, we talk about once a clique sum across K1, which is just across a vertex. So when it comes right down to it, some people call this vertex amalgamation. And that may arguably maybe the better word, but we can take it forward to edge amalgamation and then triangle amalgamation, and then we're running out of words, right? So this clique sum takes it forward to KT, whereas if you talk about vertex amalgamation and edge amalgamation, which is actually used in more papers than I thought it was, then it's a little bit limiting in as terminology goes. Now, you can't delete K1. If you delete K1, you've disconnected the graph. So the one sum and the clique sum across K1 is the same. So this is vertex amalgamation, if you wish, clique sum across a vertex, and also one sum, and direct sum. Many different names for the same thing. Mm-hmm.
When you identify that, it seems like there might be many ways doing so.
That's a really good question. Yeah, that happens in K2. So in K1, it doesn't matter. Yeah. So in K2, that's a really good question. It leads to Whitney's two isomorphism theorem. So in K2, you can actually attach it this way and this way, right? And it will give you non-isomorphic graphs. So
When we say the clique sum, we're referring to one of.
yes, we should say that's a good point, right? A clique sum, yeah. So a clique sum, yeah. So this is edge amalgamation. Yeah. And in the next talk, I will actually talk about Whitney's two-isomorphism theorem from the matroid context, and then this will come up. So we can also do this for triangles where it gets more complicated. And yeah, so this is edge amalgamation. And if you yeah, and I have not seen another term for it. So fortunately, we just have edge amalgamation for clique sum across K2 and two sum for the edge removed. And that appears to be a unique terminology. And yeah, I was writing this and stuff. If we remove the identified edges, we call the graph K-sum. All right. So this plays a big role in what we're about to do. So the next result is actually just obvious. There's nothing to prove. I just put it there as a theorem, and maybe it should be an observation. So going back to connectivity, right? So our definition of connected graph, kappa G is the minimum number of vertices whose removal disconnects G. If kappa G is 1, means literally this figure here, as in one vertex will disconnect G, so you can write G as the direct sum of G1 and G2, where G1 and G2 are connected proper minors of G. So to see that G2 is a proper minor of G1 plus G2, you just take all of that, the bubble over here, and shrink it down, and you will just get G. I'm sorry, I said it the other way around, right? To see that G1 is a proper minor, you take all of G2 and just shrink this down, okay? Yeah, David, is that okay? Yeah.
Sandra, can I quickly interrupt?
Yeah, sure.
Can you go up a little bit just to the definition of the clique? I think you wrote like it has to be a maximal.
Yes, yeah.
So you
yeah.
so okay. So in definition, the clique has to be a maximal clique.
Yeah.
Okay.
Would it cause trouble in doing the?
I mean, when you do the clique sum, they also both have to be a maximal clique.
That's a really good question. I don't think so, right?
I don't think so either.
Yeah, I don't think it has to be a maximal clique. So how should we define a clique? A clique is, but for other purposes, we need to define clique as a maximal induced subgraph, right? So
Well, maybe there could be a separation between a clique and a maximal clique.
yeah, that's better. So we'll just remove the word maximal.
Subgraph.
How about this? Does this work?
Yeah, that sounds perfect to me.
Yeah.
Thank you.
Thank you. Yeah. Good point. Yeah. You can do, for this purpose, you just want to paste it across a clique, whether there's a larger, if the clique, like, a triangle is always part of every clique. K4 is part of any larger clique, but you can paste it across that. Thank you so much, Meng Xiang. Appreciate that. Yeah. So then theorem 14, so theorem 13 is really just an observation. Theorem 14, you go one level up. So let G be a two-connected graph. Then kappa G is equal to 2 if and only if G is the two-sum of G1 and G2, where G1 and G2 are two connected proper minors of G. That's what we're going to prove now, and we might actually be stuck on it for quite some time. It's a fairly long proof. So just seeing how much power I have. Yeah. Now, it would be great if we could get some results like this for higher connectivity, but when you look at three sums, you can paste it across a triangle, right? And then remove those edges. That's what a three-sum is, correct? Over here on this side. But, this also, then this on the right-hand side becomes an issue because that graph also has is three connected, and it's kappa G is equal to 3, but it may not manifest itself as a three-sum. So it doesn't carry forward well. However, by excluding those situations, you can get something that does carry forward, but it is quite complicated. So we're just going to do the proof of theorem 14, and then we will start talking about three connected graphs. And at the end of this, we will conclude that a graph that is not three connected consists of trees, right? Series parallel networks. And let me say that again. I missed a key term. Consider an excluded minor class of graphs, and suppose you identify all of them in the class. Then all the three connected ones, and that is enough to determine the entire class, because the graphs that are not three connected are trees or series parallel networks, or the graphs that are obtained from trees, series parallel networks, and the three connected graphs that you found by doing direct sum or two sum. So in graph structure theory, and in particular, when you're finding members of an excluded minor class of graphs, we limit ourselves just to three connected graphs. All right, and this theorem is the reason. Okay, so let's do this theorem.
Does this sound like a generalization?
Unfortunately, no, because of this over here. So what happens in higher values of K? So this would be a three-sum on the left, right? So a graph that is four connected and that is three connected and not four connected could manifest as a three-sum or as the one on the right. So when we try to generalize to kappa G equals 3, if and only if G is G1 plus 3 sum G2, we have to exclude some things. So it becomes very non-trivial. And this proof too is fairly long. So, but that's ongoing research. So if you're interested in it, it's definitely worth looking into. So let's do this proof, okay? So let's do the easy side first. And Ming Chang, just please feel free to interrupt. I've actually seen this proof in a slightly different form, and I'm actually keen on getting your views on what I'm presenting.
Sure.
Yeah. So where is the other form? Yeah. So suppose you can write G as G1 plus 2 sum G2, right? So by the definition of two sum, there is this kind of structure, right? So there is an edge that you removed, right? So these two vertices become cut vertices over there, forming a two-element cut set. So kappa G equals 2. So one direction is straightforward. That's what fails over here. Because in the three-sum, right, you can have these three vertices, but you can also have a situation like this. So that's not there for two-sum. So that direction was straightforward. So now let's look at the other direction. Suppose kappa G equals 2, right? Which this means there exists a vertex cut whose removal disconnects G. Good? Okay. So let's get a picture going. Actually, I need a little bit more. Let X and Y be in two distinct components of G minus UV. Say X is in one part and Y is in, I think I'm calling it T. X is in T and Y is in G minus UV minus T. So now we definitely want a picture going. So there's our UV. And there. All right. So now since kappa G is equal to 2, one of our earlier propositions, Whitney's theorem, I forgot the numbering, implies there are two internally disjoint XY paths, let's call it P and Q, passing through U and V, respectively, forming a cycle C as shown in that figure. All right, so the figure's up there. Good so far? Right? So we have, there's a vertex cut UV whose removal disconnects G. So you'll be able to find an X in one side and a Y in the rest. And now because kappa G is 2, Whitney's theorem says there are two internally disjoint UV XY paths, right, passing through U and V respectively, forming that cycle. So now construct G1 by deleting all the edges in T outside the cycle and contracting the portion of cycle C in T down to an edge E1 incident with U and V. All right. So what are we calling G1? I believe, let's see, did I get this backwards? And I think this is okay. So you start with, you delete all the edges in T. Okay, in my picture, at least I have this. Thanks. Where did it go? All right.
So X disappears.
Yes. So what you're doing is throwing out all the edges outside the cycle, right? And contracting the entire cycle down. And what's left on the left-hand side is E1. All right. Sorry, for a moment, I was just wondering why I'm calling the right-hand side H1, but apparently that's what I am doing. So this is, I mean, G1. Then similarly, construct H2 by deleting all the edges in G minus XY minus T outside cycle C, and I'll just say contracting the portion of cycle C in G minus XY minus T down to an edge E2 incident with U and V. Sorry, say again. Yeah, G2, yes. And I'm not sure why I have H2 also, but I think there's a reason for that. But maybe if there is, I can always use a different letter. No, it doesn't matter. Yes, G2. All right, good so far? So the intuition is you just take everything on the right and contract it down and do the same. There's only one detail. Observe that each of G1 and G2 is a two-connected proper minor of G with at least 3 edges, and G is the two-sum of G1 and G2 with edges E1 and E2 identified and removed. Right?
G was the original graph.
G was the original graph.
It's missing all the internal edges cycle.
We deleted everything. So we deleted everything and contracted the cycle down. Yeah.
Right, so why is G the two sum of G1 and G2? Because it doesn't have the deleted edges anymore. They should still be.
So what we do over here is we are defining G1 and G2, right? So from the two sum, when kappa G is equal to 2, we're defining what G1 and G2 is. So in one case, so the idea is this: you start with
You're only removing them one at a time. So
Yeah.
The other side
the other side has it, yeah. So it's a deletion, it's contracting, deleting everything, contracting that cycle down, the other side is left untouched, yeah. And the only detail left, and then maybe I can just finish up with a picture, is suppose the graph, the original graph actually did have that edge UV, right? In that case, your two pieces, G1 and G2, are this. So this is E, this is E2, this is E here, and this is E1. That's the only detail. So this way, you'll have to have multigraphs in this area, right? So G1, this is G1, this is G2, or maybe the opposite as I said it. And when you stick these two pieces together, you will get, across this edge E, you will get E1 and E2. Let me say it a little bit more carefully. Yeah, let me say it carefully. Suppose E equals UV is an edge in G. With not E identified and removed, but E1 and E2 identified and removed. Yeah, that's it. Okay. Maybe I made it longer than it needs to be. Yeah.
One side is like K connected, the other one is two connected.
So one side is K connected, and the other side is two connected.
Yes, but two connected graphs.
So you're just sticking it together across an edge, right?
Yeah, but we don't get the F state. The F no F state. If K is bigger than K connected, it applies to it's being K connected is greater. K capital G is greater than.
So this, it would, you mean, what if kappa G is?
Well, I guess what does it mean by proper?
So proper minor just means that, minor technically can be the graph itself, right?
So we have to be K connected because to leave that just.
Yeah. So, I mean, we can get some kind of partial result for K equals 3, but it will have to exclude that other situation. And I haven't thought about K equals 4. So I'm not sure whether there are more situations to exclude. So the K-sum captures fewer and fewer, I think, graphs as you go higher in connectivity. But for two-sum, for two connected, it captures the whole thing. The if and only if condition. Right, David? Yeah. Ming-Chang, what do you think? Is this okay?
Yeah, it looks good.
Okay, thank you. So it's in my book, and I always get very nervous presenting something in my book. In the off chance that there's like something wrong. And in the next edition, I would clean it up a bit and maybe try and say it's slightly different. But I think, yeah, this proof will work. Yeah.
What about an example of a cycle?
Oh, that's a good question. So, what happens for cycle? Well, you know what? I think cycle will illustrate what happens in the whole thing. So this is my C, right? So, so pick two vertices U and V in the cycle, and then pick those other two vertices X and Y, right? So you literally don't have anything else except the cycle. So it's like this figure exactly as it is. So what you do is to get one side, you just take all of this, you contract all of this down to an edge. So you get this there, right? So this is everything contracted down. So it's this would be G1, which is G contract yellow edges, right? And then do the same for this. So this would be G2 is G contract green edges. Okay.
I guess something maybe I was confused about was when you do the clique sum, the edge that was now formed between U and V, where does that go? It disappears?
So in the two sum, yeah. So in the clique sum, it stays. In the two sum, it disappears. But if you have an edge, you can just do parallel edges, and so two sum covers everything. So if I just said clique sum, it would not cover the cycle. So that's why by saying two sum, it also covers the situation like this. So this is my G1 and G2. You slap them together and then remove that edge. So two sum requires the edge to be removed, but if you want to keep the edge, then you can do that too. So it's a little, so you don't have to exclude cycles or anything. So I've seen this result expressed as is this, except it's a cycle, but two sum takes into account cycles. Yeah, that was another good question. Yeah,
That's maybe a stupid question.
no stupid questions. They're all good
In
questions.
the proof, we had two components, but what if there's three components? After removing an edge, you have like three things.
Yes, yes, you can, it's, I suppose you can have any number of things. So you can have, for example, this. Yeah,
But the proof relied on us having two components.
two components. So this is also kappa G equals 2, right? So what you can do over here is you can, so the theorem states that it is two connected, right? And G1 and G2 are two connected proper minors. So if you think of it as like, you know, three petals, so maybe just first think of it like this, and then think of this. This is G1 and this is G2. Yeah, so it works. Yeah. You can also line them up like a train, yeah, and get many, you know, sort of line them up like that and break it everywhere. Yeah. Okay, so how are we doing on time? Let's see, 5:07 already. Yeah. So the structure of three connected graphs, all right? So now I'm going to start with the Wheels theorem and stuff, and maybe really just take it slow. And then wherever we stop by about, you know, 5:20, 5:30, that's where we stop, and we'll pick up the next time. And I'll have, I think next time I'm thinking of making slides, so it could go faster. So the structure of three connected graphs. So we've got all our theorems in place, and wheels play an important role in three connected graphs. The first thing to notice is the terminology that, if G has n vertices, then it's customary to put like n as a subscript, but following matroid terminology, we're going to put n minus 1 because the number of spokes is n minus 1. All right, so n vertices, n minus 1 spokes, n minus 1 rim edges, and 2 times n minus 1 edges, right? So that's W5. Now, if you delete a rim edge, I mean, there are two kinds of edges in the wheel, rim and spokes, right? I mean, there's no other kinds. I mean, we're talking actually edge orbits here, but this is simple enough that we don't need to get into automorphism group and all that. So if you remove the edge, the rim edge, you've gone from 3 connected to 2 connected. So the wheel is 3 connected. Actually, it's you can't do more than 3 connected, because if you remove 3 vertices, 3 edges, any 3 edges there, you'll disconnect the graph. So if you remove a rim edge, you've disconnected. You've made the graph not disconnected, 2 connected, right? So it is no longer 3 connected. If you remove a spoke, again, it is no longer 3 connected, because if you remove 2 vertices here, you've disconnected the graph, right? Now look at edge contractions. So if you contract the rim edge, then you've got parallel edges. And if you contract a spoke, then you've got parallel edges again, right? And in graph theory, these graphs are 3 connected. Because if a graph is 3 connected and you add parallel edges, you preserve 3 connectivity, right? I think both are 3 connected, right? This one's definitely 3 connected. Is this one also 3 connected? This one's 2 connected, okay. Yeah, this one's 2 connected. But they're not simple, okay? So this is not, so we'll present it like this, not 3 connected, not 3 connected, not 3 connected. 3 connected, but not simple. And thus, Wheels' theorem states that wheels are the only graphs with the property that G delete E is not 3 connected for every edge E, and G contract E is not simple and 3 connected for every edge E. And that's a really long and big theorem, and I'll give some references to it and even a link to a proof on the web that I thought was really nice. All right, so this is a major result. There's many ways of expressing it, and it becomes the basis for proving excluded minor results. So let's see. I'm calling this, so this is the sort of the basic one, the one whose proof that we would see. And then I'm calling this the top-down version. So we'll do Wheels theorem. Mhm. Thank you. And I also forgot something else. Three connected and simple. Yeah. With the property that G delete E is not three connected for any edge. Yes, good. Yeah. I don't know what it is with Touch theorem. Every time I say it incorrectly. But I have like 5 versions of it too. So this is the Wheels theorem, top-down version. So let G, besides the wheels, not isomorphic to wheels, be a simple 3-connected graph. Then every other graph has the property there is an edge E such that G delete E or G contract E is simple and 3-connected. And what this does is it allows you to do induction. Actually, from Whitney's theorem and those corollaries that we did, we can show easily that every 3-connected graph has an edge whose contraction is 3-connected, right? Including the wheels, right? If there's a contraction, if you contract the rim edge, it's 3-connected. The key is simple and 3-connected. So there is an edge E such that either G delete E is going to be simple and 3-connected, or G contract E is simple and 3-connected. Right? Now, I'm going to present it again as what we call a chain theorem. Once again, the same thing. Let G be a simple 3-connected graph. Then there is a sequence of simple 3-connected graphs, right? Where you start with a wheel. Am I jumping? No, this is good. You start with a wheel. Right. Actually, start with G, and you can do deletion and contraction throughout and get down to a wheel, which is why I have equals on one side and isomorphic on the other, right? Such that for every I, either GI delete E is equal to GI minus 1, or GI contract E is GI minus 1 for some edge E. So this is just another form of Wheels theorem. Every other graph, right, is going to have an edge E such that G delete E or G contract E is simple and 3-connected. Therefore, you can start with G and do these deletion contraction, preserving 3-connectivity and simple, and get down to a wheel. Not saying which wheel, right? Get down to a wheel. That's top down. Both of these versions, this is the one we prove, and they're all the same. Yeah.
The third one's.
So, well, it's saying it again and again. So, if there is an edge E such that G delete E or G contract E is simple and three connected, right? Say G delete E is simple and three connected, and it's not a wheel. Then you can, in G delete E, you can find something where it's another F where you can delete or contract and get to something smaller. If you reached a wheel, you're stuck there. That's the end of your chain.
How do I know I ever get to it?
That's the only one. That's the only place you would stop, right? And we've already done the parts where we have to, all these graphs will have a W4 minor, right? Because they'll all have W3, but then W3, you can't go anywhere. So the next step is W4. They'll all have three connected graphs will start with W4. So the Wheels theorem doesn't tell you which wheel. That's important to note. It doesn't tell you which wheel. And if you hit a wheel, then you're stuck over there because the wheels don't have this property, right? You delete any edge or you contract any edge. You won't get.
We can say that wheels are the minimal three connected and simple graphs for any.
So yes and no. They are in the sense that you're thinking of, and the way I think of it too. But we already have something called minimally three connected graphs, right? A graph is minimally three connected. A removal of any edge destroys three connected. So that's why we won't use the word minimal. Okay, so
we don't know
the
which
first.
we don't know which end.
Yeah, we don't know where we're stopping. Yeah. Yes, go ahead.
But the first version of Wheels theorem kind of implies that that's the minimum three connected simple we can expect, because after that we are stuck with the sequence of.
Yes, minimum in your sense, definitely. But remember, the prism is also minimally three connected, right? So you throw out any edge and you've lost three connectivity. So actually, there's lots of minimally three connected graphs. They have minimally three connected. They're up to 3n minus 9. I think you can have minimally three connected graphs. So there's a lot of them. But it's minimal in the sense that you're thinking of. It's just that we don't want to use the word minimal. Like somehow, like some other word that means the same thing in this context. Makes sense, Arsha?
Yeah.
So now we're going to do Nadia, is this okay? Yeah. So now we're going to do the bottom up. And for bottom up, first of all, we can do it because every graph sits in Kn. We don't have this. So all of this carries forward to matroids, and matroids you have Wheels and Wheels theorem. But we can't always use the bottom up because a matroid doesn't sit in a larger object. If it's representable, it does, and it sits in the largest projective geometry. But while we're staying with graphs, every graph sits inside the corresponding Kn. So we can grow it. But in order to do that, we have to do the opposite operations of edge deletions and vertex splits. Now, the operation opposite edge, we're already at 5:20. We'll stop here soon, okay? We'll stop at 5:30. The operation opposite edge deletion is edge addition. And that's actually easy compared to vertex split, which when you write it up carefully, as we did, is a page long, the definition. And I've just kind of focused only on the three connected part over here. But let's do edge addition. So if this is my G, taking prism graph, then if I want to add an edge between non-adjacent vertices, I will call it G plus E. Add an edge between non-adjacent vertices. And it's very clear that adding an edge and deleting the edge are inverses of each other, right? And don't do this, right? Because that's, you're kind of adding a parallel edge. Just don't do that. That's why we have non-adjacent vertices. And the point is, if G is 3 connected and you add an edge, then it remains 3 connected because you're not doing something like this, okay? Well, that would maintain 3 connectivity, but just don't do it. Yeah, you're not contributing anything by doing the green edge. Yeah, sorry?
What about K5 minus D? If we add an edge, doesn't it go too far connected?
Yes, yeah, if you add an, very good. If you add an edge to K5 delete E, then you get K5, which is a 4 connected graph. Yes. So if G is 3 connected, G plus E remains 3 connected. So a 4 connected graph is also 3 connected, right? Because the way we've defined K connected is if K is greater than or equal to the kappa, right? Oh, yeah.
At least, yeah, we
The
need
other way around, kappa is greater than or equal to K, right? Then it's K connected. Yes, thank you. Yeah. David, is that okay? Yeah. So now vertex split. And again, I mean, there's something about this operation that really requires going down into details. And I'm just focused on 3 connected graphs here. So I'll just put some conditions to maybe make it a little bit simpler. So vertex split of simple. On top of that, I'm just going to think about simple 3 connected graphs. So first of all, you need to have degree V at least greater than or equal to 4, because if it's less than or equal to 3, then you're not going to be able to split the vertex and distribute the edges and preserve 3 connectivity. So we're imposing that condition so that we preserve 3 connectivity. So you take V and you split it like this, so you get a new edge F. This is the new edge, like that new edge E that you're adding. And you distribute the neighbors of V to V1 and V2 in a disjoint manner, right? And now while G plus E gave you just one graph, G dot F, which is, we use the notation that emphasizes the edge. Even though we're saying we're splitting a vertex, we're really thinking of it as an edge operation because we want to use dots operations are edges, right? And you can get many non-isomorphic vertex splits. And that's what all this is saying. For example, and the example I'm giving is going to make it sound like it's all one, but you can, this is K5, and we split this vertex V, and there's so many different ways that you can assign A, B, C, and D to the split vertices V1 and V2. And in this case, they're all isomorphic to this one. Just a coincidence. This case, they're all isomorphic to this graph. But if you take, just making sure I do that correctly. Yeah, they're all isomorphic to that one. But if we take, our next example, suppose we take the prism with an edge. You can't split a cubic graph. Prism is a cubic graph. All the vertices have degree 3. Then you can split this vertex, right? And this vertex. And you can do that thing where you assign all, or you consider all possible edge assignments. And you'll only get 3 non-isomorphic graphs. There's 6 splits of the red vertices and 6 splits of the green vertices, but you only get 3 non-isomorphic graphs. In this one. All right, see, there are, of the 12 that you have to actually check isomorphism with, you end up with just 3 of them. So finding vertex splits is a very non-trivial task. And these are non-isomorphic. 2 of them are planar, and the middle one is non-planar. So the Wheels constructive version, so where is that theorem? From the bottom. So you start again with the graph and exclude the wheels. Then there's a simple 3 connected graph. We'll say it this way. G dash such that G is G dash plus E, or G is equal to G dash dot E. All right. So if you have G, then there'll be some graph here such that you can get up to G by adding an edge or splitting a vertex. And that's how you grow your excluded minor classes. And then the chain theorem, right? There is a sequence of simple 3 connected graphs. And the difference is now you start with a wheel and you can grow it, but you may get something isomorphic to G, not necessarily exactly the G that you started with, such that for every I, GI plus E is equal to GI plus 1, or GI dot E equals GI plus 1. So what this tells us, that if you know the wheel minor, right, then you start with that wheel and you can add an edge or split a vertex, add an edge, split a vertex, and get up to the G, an isomorphic copy of G. And then we'll stop here, but I'll just say one more thing and say more. Splitter theorem tells us that you can replace the wheels with any minor, as long as there's a few conditions, as there's no larger wheel, etc. But that's the main thing, as in, if you know a minor in your graph G, you can let's call it H, you can start with H and you can grow up to G by doing these edge additions and vertex splits. So when you're trying to characterize excluded minor class of graphs, right, when you start with, you don't know how big the class is going to be. It could be huge. The fact that so many of them are not is just amazing. That is, if you know one member in that excluded minor class, then you can start growing the class with these vertex splits and edge additions and hope to find a pattern that will give you all the members in the class. Now, I want to add one more thing, that the graph minor theorem gives us a structural characterization of graphs with no specific minor H, but that's a theoretical result, and you can't actually use it to find specifically members of excluded minor classes. But we know that we can in theory, so it's a good thing to look for it. Now, what happens is the class is very large oftentimes, and in that case, we want to raise the connectivity. So ongoing research is to develop these kind of theorems for four connected graphs, because then, classes will have fewer four connected members, so you can figure out all the four connected members. And so it goes. This is a good place to stop. Mingxiang, how did it seem?
Sounds good. Thanks for the talk.
Sounds good.
Very nice talk.
Everything correct?
Yes.
Everything correct?
Looks good to me.
Okay, thank you. Thank you. I really appreciated that. And that's actually why I wanted to present it. I just wanted to think it through and get some feedback. Yeah. So all good? We'll stop here. Arshia, good?
Yes,
Okay.
Sandra.
Thank you. Yeah. So next, maybe I'll make slides, because we'll start talking about excluded minor classes and stuff. And slides is better for that. Yeah. Okay. All right. Okay, then I will close the Zoom, and we'll meet next Wednesday. And Anna Pan is going to be speaking after spring break, and she's going to be doing lattices, which in other words are matroids. So it's really exciting. Yeah. Okay. Thank you so much, Arshia and Mingxiang.
Thank you, Sandra.
Thank you,
See you later.
See you. Bye.
for the talk. Take care.
Bye. Thanks. All right, so that's another one went off well. Yeah, thank God. Yeah, I get so nervous in this one. Oh, yeah, it's not very cool. Okay. Did I stop the recording? Stop recording.